The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. We've had a lot of requests lately for us to talk about CNC machines, so I thought that'd be a good topic for this episode. Now, a CNC machine is a computer numerical controlled machine. Granted, a paper printer or a 3D printer or even a modern washing machine is controlled by a computer, but CNC usually means machines that have a bit that mills material out of a stock. Those machines will have an XY Cartesian system with a 0-0 home. Basically, you'll move the head over to 0-0 and all of your designs will go from that point inside of a bounding box of some kind. So XY, much like a 3D printer. Then on the arm, there'll be a motor or a spindle on the Z-axis, which means it goes up and down, with a cutting tool, and that's what will actually cut into the material, creating your shape. It's a subtractive method of creation, which means it's removing material, subtracting it from stock in order to create what you want. This is in contrast to a 3D printer, which is an additive process. It's adding material to a base to create an object. The advantage there is you don't have to add all the material for something large like a desk. You only remove the parts you need to reveal the pieces. CNCs are good for larger objects, as I just mentioned. Things that need to be stronger. You can cut things out of wood, plastics, metal, whatever you want really, as long as you're conservative with your bit speeds. The build times are faster. Just making one cut to remove a big piece, it's a lot faster than trying to 3D print all the layers of a big piece. And you can also do PCB milling with it. You can take a blank copper piece, put it in a CNC machine, use a V-bit, and trace out the circuits that you want to make. For today's example, we're going to be using a Shapeoko, which is an affordable desktop CNC machine. We'll create an object to make with the machine, go over all the parts of the machine, turn that object into G-code, and then cut it out. Let's get started.
Amazing hacks.
How can we make this portable?
Inspired designs.
I am the internet troll.
Regrettable acting.
Batten down the hatches!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Let's go over the parts of a standard CNC milling system. First, we have a power supply. This is a 24-volt switching power supply. 24 volts is the voltage used for the stepper motors, and that voltage is knocked down for the driver board, which is this right here. It has a microcontroller on it, a bunch of input-output, a USB connection, and these 4 plugs are for the 4 stepper motors. So we have actually 2 Y motors. That way it's basically easier and cheaper to put a motor on each side and drive them at the same time than to try to make a linkage for a single motor. So we have all this ported out nicely to some plugs in the case here, and they're nicely labeled so we know where everything goes. There are also some plugs for limit switches. We may not have to use limit switches on this machine, but what a limit switch does is when the machine homes, it'll go all the way one way, click, oh, that's my limit. All the way another way, click, that's my limit. Oh, now I'm home. So we can hook those up here if we want. One thing of note is you don't want to move the head manually very fast if the machine isn't on, because you're actually generating current in the motors, and that current will be fed back into the system, which it's not really supposed to be. So always, if you have to move it manually, always move it slowly. And if you're transporting it in a car, make sure that you have everything inert. Otherwise, like if you take a turn and this goes, right? You could send too much current back and destroy one of your integrated circuits. Those are the kind of things you need to think about when you're using CNC machines. We go from the driver board to the stepper motors, and these are what really make the machine a CNC machine. These are direct drive motors. The motors are connected directly to the belts. Some machines will have gearboxes attached to the stepper motor. It'll look like one solid unit, but you'll have a lot more torque with something like that. This is a smaller system, so you're not going to have that. Again, there's 2 motors for the Y, and they basically are inverse of each other, so when you activate them, they both go in the same direction. So that makes it a lot easier to do. We have a linkage here for the Z. This is the Z. Can't go very fast with it, but this goes up and down and it drives our tool. This is a DeWalt, looks like a trim laminate router. They're pretty reasonably priced, usually under $100, but they're very loud. That's something to think about when you're deciding what kind of motor to get, what kind of machine to use. You know, you're gonna hear that loud noise for like 30 minutes or an hour if you're routing something, so you need to think about your spouse, your neighbor, your kids, your pets. You know, noise is something to take into account. Or you could soundproof your garage, I guess. That's always an option. The stepper motors drive some sort of toothed, accurate system that will move everything back and forth. In this machine, there are inert belts, and the belts are connected to pulleys, and when the pulley turns, it causes the machine to move along the belt. So it's kind of like a rack and pinion made with a flexible belt. There are also machines where the belt will loop at the end, although you won't have as much torque with that. You'll also see machines that have threaded rod. It'll be basically a long threaded rod, and there'll be a captive nut on that. And when the rod rotates, the nut will move the entire system back and forth. You get a lot more torque with something like that, but the speeds are a lot lower. But this belt system that they have here, it's a pretty affordable way of doing it. As long as you keep everything tight, it should be okay. Although you want to be careful with your torque. If you try to move this too fast, the bit won't be able to cut the material quickly enough, and this will bind up. Basically, it will be the failure point, and you'll lose steps, which means the machine won't remember where it was. So if it makes a circle, it won't return back to the correct spot. So it's always about moving the machine at a speed that is safe for your cutting tool and your bit and your material. For these machines, it's more about not breaking the machine or the bit rather than the part itself getting mucked up like it might be with a 3D printer. This part that I'm moving here is the Y arm. It's what the Y motors activate. It's also the Y axis of the machine. Basically, Y is usually up or down, just like in a Cartesian graph. And that shaft moves the X axis left and right, which is this. Again, I'm not moving it very quickly because I don't want to send energy back to the driver board. And then finally, on our X axis, we have the Z axis, which plunges up and down into the material. There are some machines where this will move back and forth, but instead of the whole gantry moving, the piece will actually be moved back and forth. It just kind of depends on how the machine works. This I like because it's, you know, it's very simple. One reason a machine might move the material back and forth instead of this large gantry is because everything you have on the gantry adds weight. So what this motor has to move isn't as much as what this motor has to move, and it's not as much as what these motors have to move. Of course, there's two of these. You know, these motors have to move all of this weight, whereas this motor just has to move this weight. So yeah, it's kind of about distributing the weight. But I like these systems just because it's more straightforward and you don't have to worry about the piece moving in and out and clunking against stuff. So the heart of the machine is the cutting tool itself. And you want to basically use the best cutting tool you can afford because you'll get a higher speed, lower noise, hopefully, and the bit will rotate in a straight manner. If you think about like a crappy drill from like Harbor Freight, sometimes the bits, you know, like who wants that? So you want a good tool and a good bit. And you also need to think about how much cutting depth you're gonna get. You're limited by the travel of the tool, and you're also limited by the length of the bit. In fact, the length of the bit is the biggest limitation. You can get like bits that are like, you know, inch and a half long, you know, fairly long bits, but you have to be concerned about breakage. Like the longer the bit is, the more it can wiggle, the more it can shatter. The more it will wobble at the end. So I typically like to use the shortest bit possible for the job. Most of my bits on my big CNC are only like ½ an inch long. And I just design according to that, and I very rarely break them. Let's create something to make on the Shapeoko. About 6 by 3 inches, that's a reasonable size. I'm gonna create a bounding box, which will represent the piece of material that I'm gonna use. And then inside the bounding box, I'll type my name. It'll just be like, you know, grade school, where everything you make has your name on it. The most important thing to think about with CNC milling is the shape of your bit. Bits are round, so anything you do has to work with a round bit. So for starters, I'm going to use this VAG rounded font so I can make my name and it will work with the curves. So I will make a circle the size of the bit, which is an 1/8 inch, and I can check that it will indeed cut everything. Yeah, that should work nicely. So basically, you know, what we see is what we'll get. Let me bring this up here. I'll make another bounding box around my name. Okay, and then I'll make sure everything is no color, just a solid stroke. It doesn't really matter what the stroke is. There we go. I'm gonna do an example up here to show you why the shape of the bit's important. Let's say you had a square that was 1/2 inch, right? Now, if you were pocketing this or cutting it out with the bit on the inside, you wouldn't get a square shape because the bit is round, see? The resulting cut would look like this. You'd have rounded corners, and yeah, maybe that's what you want, who knows? But it might not be, especially if you want to make something slot into it. It wouldn't work, because if you tried to slot a square object into an object with rounded corners, well, like that one song, a circle won't fit where a square should be. Wow, I just quoted, who sang that? Firehouse? So what I like to do is make slotted tabs. So I'm going to make a circle that is slightly larger than my bit, so 0.13 inches. I'm going to put this in all 4 corners, and now I'll combine it. So now when this cuts out, the bit will go along on the inside, and it will leave a clean space for your square tab that you put into it. And you can actually make it a little bit more aggressive than that even. If I take this 0.13 circle, I rotate it 45 degrees, and I will just put it into the corner like that. See? As long as enough is cut out to allow the square edge to fit, you're good. So, you know, be creative. You've probably seen these shapes on things I've cut on the show before. So here's our name tag. I'm going to save this as an SVG, which stands for Scalable Vector Graphics. It's kind of a, I don't want to say generic, but it's a standard form of graphics that are easy to open. So I can open this vector file with a web browser, for instance. I'm going to pass it through Inkscape. Inkscape is kind of the go-to program for hobbyist vector art because it's free. So a lot of the programs assume that you use it. So Adobe Illustrator specific things might not actually work, but Inkscape will. So if I pass my file through Inkscape, it will help it conform to the next steps of this project. I'm just gonna make sure everything's ungrouped. Looks like it is. Make sure these things are paths, not objects. Okay, I saved this as an SVG again. Now we're ready to create some G-code. I'm gonna power up the CNC machine. Okay. And plug it into my computer. Now there's a really cool online tool called Chili Pepper that you can use to drive machines that are based off Tiny G, such as this one. We start with a program called JS Cut, which will actually create the tool paths. And this is all online, so yeah, check it out. Over here, we have the material depth. The Z0 is going to be the surface of the material. That's how I usually do it on my other machine, so that sounds good. And yeah, this is an online app that has all of the same kind of settings that you've seen me use before using my CNC machine. 0, lower left. So I'm gonna go over here and open the SVG file that we made on the other computer. Now see how the bounding box gives it an overall shape, even though the part we're gonna cut is smaller than that. Now here's the cool part. It's really easy to make tool paths with this. We select on the objects. Come on. There we go. Okay. Okay, we're going to create an operation, which means something that we want the bit to do. We're gonna select pocket, 1/4 inch deep, generate. And this thing even has a G-code simulator, which is pretty awesome. See, it'll show you exactly what it's gonna do. It's even in, look at that. You can even look at it in 3 dimensions. Very cool. Okay, I'm gonna go back to the edit toolpath. I'm gonna select this outer box and I'm going to create another operation. And this is going to be outside. So the bit's gonna go outside that line. And I'm not gonna cut it all the way out, but let's just do 1/4 of an inch again, generate. We can go back to simulate G-code and this will show us everything that will happen. So that's actually what the bit will do. Okay, so the Z0 will be the surface of the material, you gotta remember that. 0 lower left, sounds good. All right, cool. I'm gonna go to save G-code. I'm gonna save it locally on my computer. Let's call it Ben nameplate G-code. Save as local file, I'll just put it, that's fine, let's put it in the software folder. Cool. So we've used an online tool to create G-code. Very nice. Okay, I'm going to run this program that I downloaded from the Chili Pepper app, the serial port JSON server. This will allow the web browser to communicate to the serial port and to the CNC machine. Let's go back to the Chili Pepper page. All right, so down here we do connect to hosts, we do connect to local host. Okay, now that program is letting us see, or letting the web browser see the port. So let's connect to that. All right, we should be connected to the board. Let's try to do something. Let's do 10 millimeters for every move. Cool, looks like it's connected. Now, when you're setting up a CNC machine, you want to take into account the revolutions of the motors and the pulleys and your gearing. For instance, you need to know what the step of your motor is, such as 1.6 degrees per step, and then how many steps there would be. I believe that would be 120 steps per revolution. So your code will know how many steps to initiate in order to move a certain distance. And what I usually do is I make a paper pattern of 10 by 10 millimeter grids, and I move it around 10 millimeters at a time, and then I can see that it's actually moving the right distance. So it's a combination of your motor steps, the micro stepping that your board is set to, and your pulleys and your toothed gears. Because you have to think that when the pulley's diameter times pi will tell you how far it will move with one revolution. So you have to put all that stuff in. I've already dialed that into this one, so it should be pretty good. The one thing I do want to do is set a 0 point. And I'm actually going to put the material in first before we do that. So I'm going to move the machine. Clear, all right. Now here's some engineering foam that I'm going to use. I'm going to put it right in the middle. Now, one of the most important things with mechanical CNC is holding your workpiece in place. You know, on my big CNC machine, I'll use screws, or there's a vacuum feature that it has. This is a little bit more limited. So what I'm going to do is I'm going to actually just blue painter's tape this foam block in place, just so that it doesn't move. The bit should cut through this foam like butter, so our clamping method doesn't have to be super strong. One thing a lot of people will do is they'll make a CNC machine like this and then use the CNC machine to make parts for a better CNC machine. So it's like immediately self-replicating. All right, I'm going to go and grab the G-code that I created. All right, now this is pretty slick. There's a preview on here that shows you what it's gonna look like. You can see the tool path and the depth. So right here you see that it's going to do 2 passes to make the name, and for some reason 3 passes to the outside cut. So I'm going to set a Z0 position in this block of foam. That should work. There is a electrical plate we can use to complete a circuit between the bit and a plate to set the Z depth, but we're having some noise issues with this unit, so I'm just gonna do it manually. When we generated the G-code, we said that the top of the material was 0, so that's what I'm gonna do here. That looks pretty good. Maybe just up just a hair. Okay, I guess we can check by moving other things around and see if it scrapes the tape. That looks pretty good. All right, so I'm gonna go back. I'm going to hit 0 out, which will make this 0, 0 point. So even if I were to raise the Z or move the X or move the Y, if I say go to 0, it will move back to its original position. Okay, we're ready to start the tool and run the G-code. As I mentioned, these things are kind of loud, so I'm gonna wear my headphones. Well, these are actually noise blocking headphones. There's no audio in them. All right, the milling's done. I'm gonna move the tool out of the way, clean it up, and we can take a look. Probably could have done a better job taping it, but whatever. It stayed in place pretty well. That worked out pretty good. Let's do a quick overview of CNC milling. CNCs are good for making large shapes out of large flat stocks, using strong materials like wood, plastic, or metal. And it's also really good for milling circuit boards. However, CNC machines are not as good at small objects because they're hard to hold in place, things with inside shapes such as screw posts or inner chambers, and complex 3D objects in general. They're easier to do on a 3D printer until you get into like really advanced CNC machines, but nothing on a tabletop model. And some final CNC tips. CNC machines are roughly the same cost as consumer grade 3D printers, so you could go for one or the other, your choice. Holding down the material and not breaking the bit are the two most important things when it comes to using CNC machines. You have to think about those things the most. Finally, you should take motor noise into consideration when choosing a CNC machine. They can be pretty loud, so what will your neighbors, spouse, kids, pets think? You can get spindles, which run at a higher frequency than a standard router motor, but they're a little bit more expensive. That's all the time we have for today. Be sure to visit element14.com to keep track of future builds, upcoming episodes, and special events. We'll see you next time. Starting Craptasia. Manually. I'm awesome. Craptasia is running. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.